So, welcome to lecture 5. In some sense, this is the first lecture in the second half of the class, and we're going to switch to a new class of online learning problems called multi-arm bandit problems, in the sense that so far we have been thinking about a learner that makes decisions sequentially, but receives what I call full information feedback, which means you exactly know what was the environment that you interacted with right after the end of the interaction. But then in many settings, starting from multi-arm bandit and then getting extended all the way to reinforcement learning, we are thinking about the environment where they give us some partial feedback. So one type of feedback is essentially what you get. What does that mean? So I'm picking an action, maybe generates reward, or maybe I incur loss. And then the only feedback I receive is that one number. The reward I get or the cost I get. Another question is this: in this environment where you have this kind of like partial feedback, how you can do online learning. That's the main topic. And then you can start thinking about various problems. So one is similar to what we have been studying so far. That's the full information adversarial multi-arm bandit problem. And that's the topic of today's lecture, where I make no assumption on how the rewards or costs are generated. Essentially, there's an adversary, a second player who is adaptively generating reward functions or cost functions. And then later on, starting from next lecture, actually starting from the end of this lecture, we are going to look at a more restricted environment where I'm turning the hands of the adversary to only draw reward functions and cost functions from the same distribution. That's the stochastic multi-arm bandit problem, where basically rewards and costs are IID across time for a given R. And then we will see that we can do more. And actually, there are simpler algorithms that they can achieve the optimal information theoretic bounds in those rigor bounds in those problems. But also, one thing that we are going to do in this class is trying to bridge the two worlds. So on one hand, we have adversarial multi-arm bandits. Then I make no assumption on the adversary. On the other hand, I have this stochastic setting. And when you look at the information theoretic lower bound, I'm going to talk about them today, there is a huge gap between that. There is an exponential gap between the two. So one thing I'm going to show you that there is a unified view. In particular, there is actually a unified algorithm that can achieve the best of both worlds. It can give you both optimal information theoretic lower bounds without making an assumption on which endpoints you are at. And in fact, not only that, it can smoothly interpolate between the two. So if you have this other type of problem instances called adversarially corrupted stochastic multi-arm bandit settings, where essentially adversary should give you IID reward functions or cost functions, but then there is another adversary that can corrupt some number of the rounds bounded by some given number, let's say C. And then the question is, in such an environment, what is going to be the optimal rigor bound you can achieve? So as you vary C from 1 to capital T, you move from one extreme point to the other extreme point. It turns out that this unified algorithm, which you already have learned, that's the online mirror descent, can give you the best bound in all of the points in between the two endpoints. And then after that, we're going to switch to some other paradigms in multi-arm bandit, in particular, what would happen if we are designing incentive compatible bandit algorithms, whatever that means. I'm going to define them later. And then we're going to talk about some applications of multi-arm bandit, and in particular in dynamic pricing and online auctions. And we see more of mirror descents there. And then there is this one last lecture that I haven't yet decided what to teach. So we might think about some other forms of feedback, but that's to be determined. Yes.
When you see a unified algorithm, does the algorithm see this C or no? It doesn't need to.
Cool. So one thing I'm planning to do today, last time we talked about online mirror descent, and I feel there has been a lot going on, and for especially people that they hadn't seen online mirror descent before, maybe it was a little bit too fast. So one thing I'm going to do is recapping the basics of working with online mirror descent. I'm going to show you some bounds, and then we're gonna look at the special case of today's lecture, which is multi-bandit problem, not the general uneconomic optimization, which was the setting in which we introduced on linear descent. And then after that, we're going to switch to the actual problem, right? So let me start by this recap. So if you recall from last lecture, we talked about an algorithm called online mirror descent, which you should really think of it as not just one algorithm, actually a family of algorithms. They are parametric with two parameters, let's say eta, the learning rate, and then this function f, which think of it as a mapping from Rn to Rn. So this function, the mirror map, the Legendre transform, also goes by the name of mirror map sometimes, had a couple of properties. I'm not gonna write them again on the whiteboard. So one thing in particular that's important, it is gonna be a strictly convex function. It doesn't need to be a strongly convex. If it is a strongly convex, it's actually good. But for the vanilla version of OMD, you just need F to be a strictly convex. And also it needs to kind of have divergent gradients, meaning that if you look at the gradient of F, there should be one direction that if you move along that direction, the gradient becomes infinite. The norm of the gradients becomes infinite, becomes bound. And this function was defining this picture. So you have a primal space, and then there was a dual space, and they were connected by each other through a one-on-one map. So given a point in the primal space, let's call it A, we are applying the gradient of F, which you should think of it as a map from, again, Rn to Rn. Everything is in Rn. And then you can always bring back points from the dual space to the primal space by applying the inverse of this map, gradient F inverse, which turns out to be the gradient of the convex conjugate of F. All right, so that was kind of like the primal dual picture. And what was the algorithm doing? Let me write it down quickly. So OMD, the full information version. So first we are going to initialize by selecting A1 such that it is minimizing our function f of A, and A is in our action set. And for the sake of this lecture, let me write it somewhere. So today's lecture, we are thinking about basically online learning with finitely many arms, which is a special case of online linear optimization, which is a special case of online convex optimization. So online learning with finitely many arms, and just some basic notations. So we are thinking about first reward maximization. So far we have been thinking about minimization, but for now, let's actually focus on reward maximization. Nothing is really different. So there is R1, R2 to R capital T vectors in Rn that are selected by the adversary. We have N arms and T ranks. Okay. So you have N arms, the T rounds, the decision maker essentially in each round is picking one of these arms. At every time, each arm has a reward. So RT of I is going to be a reward of arm I at time T. And these rewards are selected adaptively by an adversary. And in the full information version, they're going to be revealed after each round to the algorithm. Okay, so that's the setting. So now if in this setting, I want to run a linear descent, I implicitly assume that my action space in a linear descent is the n-dimensional sequence. So you pick a distribution as a decision maker. Once you select a distribution, you're going to sample an arm from that distribution. So I'm going to initialize A1, my first distribution, to be the minimizer of the Legendre transform. Then from time t all the way to capital T, here's what we are going to do. So first, I'm going to select, say, IT drawn from my distribution IT. Then we are going to do the update. So so far you have 80, you want to find 80 plus 1. Then there are two steps. I'm not sure if I called them this thing last time, but let me call them the gradient step, where I'm doing the following. So I'm going to define a vector wt plus 1 such that gradient of f at wt plus 1 is equal to the gradient of f at points at. And so basically, I'm moving my points to the dual space using the gradient map. In the dual space, I'm doing gradient ascent, right? So this is a maximization problem. So I'm going to add eta times RT to this vector. So these are n-dimensional vectors, right? So this is also a vector in Rn. I'm going to add them. And then the resulting W might be outside of n-dimensional simplex. So you have to do a projection step. I'm going to basically let AT plus 1 to be the minimizer of the Bregman divergence with respect to F of A and WT plus 1. So I'm finding the point in n-dimensional simplex that has the minimum Bregman divergence with respect to WT. And just as a reminder, so df of two vectors x and y is defined to be f of x plus f of x plus f of y minus f of x minus f of y, plus minus f of y minus x minus y dot product gradient of f at y. There are some cool identities. Let me actually write some of them here, just in case that they turn to be helpful in today's lecture. So for example, one is that if I look at the Bregman divergence with respect to the conjugate function. If I look at two vectors x and y, then you can show this is equal to Bregman divergence of gradient of f right, f inverse or gradient of f star. Let me just leave here. Gradient of f star. So if I have 2 points in a dual space and I want to find their Bregman distance, then I can map them to the if you have 2 points in the dual space, I can map them to the primal space. We get their actual distance using the original Bregman distance. So Bregman distance of x and y with respect to conjugate function is the Bregman distance of gradient of a star of y and x. So you have to swap. This is the asymmetric operation. So that's one helpful identity. Right. We'll make sure I'm not making a mistake here. That's right. All right, so what else that might be helpful? I think I already mentioned that the gradient of f inverse is gradient of f star. I think that's it. So this is defining the algorithm. And then what we showed last time is the following theorem. So theorem that really goes back to original work of Nemirovsky, OMD theta and f has the following regret bound. The regret after t number of rounds, let's define it as it's a maximization problem. So I'm going to look at let me define a slightly different notion. So regret t and some action fixed action A, which is the regret that the online algorithm receives with respect to playing the fixed action A in all rounds. So this is going to be equal to basically summation of RT dot product A, and imagine you can have a randomized action, even though optimal fixed action in hindsight is going to be the deterministic one, but for now, let's handle randomization. So this is the benchmark minus what the algorithm gets, which is summation T from 1 to capital T, RT dot product AT. And then we showed that this is going to be upper bounded by the following quantity. Basically, f of A minus f of A1 divided by eta plus 1 over eta times summation T from 1 to capital T. We need to look at the Bergman divergence of A T and W T plus 1 minus the Bergman divergence of or Bergman distance of A T plus 1 and W T. And these two terms are quite important every time that you analyze mirror descent. Let me highlight them because we need them when we talk about the multi-harmonic problem. So this term typically is called initial divergence. There is a different view for mirror descent using follow the regularity there. So if you have that view, if you have heard of that view, usually this term goes by the name of regularizer penalty for those that they have heard that, they have seen that version. But for our application, this is really about the initial divergence between your first action and the target action. So this is what we call the term initial divergence, or people call that initial divergence. The second one, typically called local norm. And again, with the regularizer, follow the regularizer leader view of OMD, this term also goes by the name of the stability term. And the name of the game is really trying to bound these terms ideally in a balanced way. Because if you have any sort of imbalance, maybe there is a better choice of the learning parameter, or maybe there is a better choice of the mirror map that you can balance the two terms. And it is almost at the level of an art, how to design an online mirror descent, how to pick the right mirror map, how to pick the learning rate. And there are some flexibilities, which I'm going to talk about soon. For example, you can have time varying learning rates. And then that makes it a little bit more complicated, but more or less the same. The combining that with choice of mirror map and then trying to guess how to balance these terms depending on your application is really the art of designing OMD. Some people are really good at that, some people are not. So one thing I'm trying to cover is some of these ideas on how you can actually design those OMDs. Before getting there, let me try to give some other bounds and describe them last time as well. So one thing that you can say as an upper bound of this term is that I can get rid of these Bergman distance because Bergman distances are non-negative. And then focusing on this term using this identity here, I can say it's going to be at most FA minus F of A1 divided by eta plus 1 over eta from T from 1 to capital T. So now I need to look at the right, so df of ATWT plus 1 will be equal to the df star of gradient of f applied on this thing and gradient of f applied on that way. So, but we have to swap them. So gradient of f at the point WT plus 1, if you pay attention, this is basically gradient of f at the point AT plus eta times RT. And then the second term is the gradient of f at the point AT. So now, for a second, assume this term did not exist. Then it would, you will have received the 0 here. So somehow, And then, okay, so eta, you should really think of it as a small number. So it's going to be 1 over a square root t, some learning it is small. Somehow you really want this function, f star, be such that the Bregman distance with respect to f star to have some sort of smoothness, Lipschitz continuity. So as long as this is a well-behaved function, then you can have a control over a star. And this is typically the assumption that, like for example, just shoot you one assumption that is usually helpful. If you assume f, the original mirror map is strongly convex. There is this theorem in convex optimization that says if a function is strongly convex, then its conjugate function is going to be, let's say the function is mu is strongly convex, then the conjugate function is going to be 1 over mu Lipschitz smooth. And then Lipschitz smoothness will result in this quantity to essentially be bounded by something like 1 over 2 mu times the norm to distance of the two. And the norm to distance is a good term because you can have a control over that. So, for example, if f is strongly convex, usually you have stronger bounds, but that's not a necessary condition. To see what we can do with this, let me show you a couple of useful bounds. And one of them is related to that strong convex. Yes.
Quick question. Something that confuses me is this function f. So we are trying to maximize sum of rewards, right? This theorem holds for any f, right?
For any f, as long as it is a Legendre transform, there were a couple of assumptions on the Legendre transform. It should be strictly convex, and its gradients should diverge to infinity when you move along this specific direction.
And so when you say argument of f, like in initialization,
Right.
is it like some norm of because it's a vector, right? F of a.
F of a, the reason is
Okay.
that's the convention. It's a scalar function.
So okay, f can be like
F is negative entropy.
got it.
That's called like Leibniz divergence, right? The Bregman divergence is going to be called like Leibniz divergence. So if it is negative entropy, then I want to pick a point in the simplex that minimizes negative entropy, which is maximizing entropy, and that's the uniform distribution. This is the reason that in exponential weights we start with uniform distribution at the beginning. Okay, thank you. This was critical. All right, so let me show you some bounds, right? So bound number 1, what you can get in the multi-arm bandit problem using OGD. OGD, multi-arm bandit. And for now, we're taking a full information multi-arm bandit. So just as a reminder, f of x is going to be equal to half norm of x squared. All right, good. Now, let me use some abbreviations. I'm going to call this term initial divergence ID. I'm going to call this term local norm throughout the lecture. So what can we say about our initial divergence? Initial divergence is going to be bounded by essentially 1 over eta times norm 2 of A, right? And A is a point in the norm 2 squared. And A is a point in the n-dimensional simplex. What's the upper bound on this norm 2? 1, right? So like integral points in the simplex, they have the maximum L2 norms, but this is upper bounded by 1 over eta. Somehow we do a very good job on initial divergence. Like you can actually show OGD gets the best initial divergence among all the first order elements, and this is really good. But then the issue is in this term. So let's think about that. For example, if I look at the local norm, then using this upper bound, the Bregman divergence for this mirror map is half of the norm to distance squared. And the gradient map is the identity map. The gradient of f at x is equal to really x. So partial f is from Rn to R, but gradient is from R n to R.
Right.
So, gradient map is going to be identity map. That basically means that this term is just is 1 over t summation t from 1 to capital T, half of the L2 distance of these two guys, which is half of the L2 norm of RT squared times eta squared, which is equal to, I should have mentioned that as my assumption here. So we assume the rewards are bounded. I constantly forget this assumption. So RTI is going to be between the 0 and 1. Then this norm 2 is going to be bounded by what? Just n, right? Because each RTI can be 1. I don't say that I'm the L2 ball, which is the hypercube. So each component can be 1. So this can be at most n. So that's going to be upper bounded by eta divided by 2 times n times t. And then if you balance the two terms, the regret would be essentially upper bounded by over there the square root of nt by selecting eta to be, let's say, 1 over the square root of nt. That's the best thing we can do. But you already know for full information learning, this is not a good bound because we can improve this n to log n. We saw that in lecture 1. The number of arms should not appear in the square root form in the regret bound, it should appear in the regret form. So that brings me to bound 2. Recovering our first lecture, exponential weights Baltimore Bandits. So f of x for this particular case is going to be generalized negative entropy, which is a summation over I, xi, ln of xi minus summation of xi. So points in the simplex, this term is going to be 1. And that's actually important in our analysis. The Bregman divergence is the generalized callback label divergence, which is sum over I, xi, ln of xi divided by yi, minus summation of xi minus yi. The gradient of f is ln of x, and if you remember from last lecture, this is the reason that we will have the exponential optics. Because if you apply the gradient, you take log from wt plus 1 at, and then you're adding something. If you take an exponential function from both sides, then basically that's going to be wt plus 1 is equal to at times e to the power eta times alpha. And that's what exponential. And the inverse of this guy is the exponential function. And these are the vectorized version of the log expression, which means that every component is ln of xi, but you have an n-dimensional vector. So forget my notation. All right, so now with this, what can we say about initial divergence? So initial divergence is going to be at home. So you're trying to maximize this quantity for points in the n-dimensional simplex. For any point in the n-dimensional simplex, you're trying to minimize it. This is going to be 1, so it does not appear. It doesn't really matter. So you have to minimize negative entropy, which means you have to maximize entropy. And entropy will be maximized if you have a uniform distribution where the quantities that you get log n minus 1, I'm going to get rid of that minus 1, divided by eta. All right. Make sense?
Wait, f of a2?
F of, that's f of a.
So f of a1 was the R. A was a constant that someone else chooses, right?
That is true, but the still f of a, regardless, is going to be
Higher. Because we are
that's a good point. So I guess your point is that answer to your point. So here's how I would answer your point. So if you look at deterministic distribution, so think of A as being an R. Mixed strategy is going to be a little different, but let's say A is an R. Then for that particular R, this quantity is going to be zero. The entropy of point mass is zero.
Right.
So this quantity is going to be zero. So my other point is that how did you get it? Let me actually show you. So here you're right, absolutely. It's a implicit I'm assuming that A is just an R. So it is the indicator that it is EI for some RI. In that case, f of EI minus f of A1 divided by eta is going to be equal to 0 minus f of A1 divided by eta. And then this is equal to log. Well, so it's 0 minus some 1. And then this guy also has a 1. So that means this is going to be minus 1 minus f of A1 divided by eta. That's going to be log n.
because the pure arm has the maximum entropy, right? Yeah.
Pure arm has the minimum entropy. Entropy is 0.
Okay. Yeah.
But then the uniform arm has the maximum entropy.
Yeah, that was a negative.
Right. So I'm maximizing the entropy, which is equivalent to minimizing negative. The more interesting term is the local norm. So okay, so just to compare the two terms, you see, in terms of initial divergence, OGT is doing a better job. But in terms of local norm, exponential weight is doing a much better job. So local norm is going to be, I'm going to use in fact. Going to be at most 1 over eta summation t from 1 to t df star of gradient of t plus eta rt and gradient of f a t. And I haven't told you what's actually that Bergman diversion, so the direction I'm making df star of some x and y we can show is equal to sum over I. Sure. Right, so it is e to the power yi, right? Sum over I, e to the power yi times e to the power xi minus yi minus xi minus yi minus 1. A little bit weird and seems maybe it's hard to work with these terms. So remember this gradient is log, right? So gradient of f at at is the ln of at. And this is basically ln of at, which is the vector itself plus eta rt. Now I have to look at the e to the power of ln of ATI. That's ATI. So it gives me summation I from 1 to n ATI. And then I have to look at e to the power of yi minus xi. Okay, so what is yi minus xi? So this is my y, this is my x. Yi minus xi is just going to be eta rt I. So this is y, this is x. Look at the difference of the two vectors. The coordinate I is going to be eta times RTI. I have to look at the e to the power of eta times RTI. So it's going to be ATI e to the power of eta times RTI minus yi minus xi, xi minus yi. That's it, xi minus yi.
Minus xi minus
Minus xi minus yi, but so this is xi minus yi minus eta RTI minus 1. Right, so this is the upper round. Does this look familiar? Are you guys ready for your midterms? This is exactly the bound that we got in first lecture. If you look back, so we use this potential function argument, and then we had several steps, but eventually that was literally a final bound that I get. And if you remember, I used this inequality, which I very much liked, that e to the power x minus 1 is at most x squared. For any x, I believe. But in particular, when x is between 0 and infinity.
It can't be. Isn't it the other way? Maybe. Because the left hand side is your exponential.
Between 0 and 1. So. Right. Between 0 and 1. The reason is if you look at basically, so at x equal to 1, the Taylor is. And so this is like half of x squared plus other thing. And that other thing is at most 1. So if you change the coefficient to 2 to 1 instead of half, then you're good. But if I want to give you another proof, I would say at x equal to 0, both hand sides are 0. Let's look at their first order derivatives. So left hand side is going to be e to the power x minus 1, and then the right hand side is going to be 2x. So I want to say from 0 to 1, this is always a smaller one. Why? Because again, take another derivative, so it's going to be e to the power x, this is going to be 2. Well, so maybe, yes. Right, so you're right. So e to the power 1, 2 is larger than 2. Let me make it half to make our life easier, because that's really what I need. Because eta is 1 over square root of.
For 1 was correct. It's e to the e minus 1 is at most 1.
No, but
I mean the inequality.
I see. The inequality itself should be correct. E to the power 1 minus 1 should be smaller than 2, but my proof does not work because, yeah, so okay. Anyways, you get the point. So this should be true. My proof, yeah, they done your proof for this, can't be sure. You can use Taylor expansion and then bound that there. And then you get this.
But x2 over 2 also works for you.
No, so x2 over 2, then the left hand side will be larger than the right hand side. Look at the Taylor expansion of e to the power x. The half plus some constant would work. That's why I changed it to 1. If you want my proof to work, change this to 2, and my proof is going to work. All right, so the point is, this is going to get from summation I from, there's a summation over t as well, summation over t, summation I from 1 to n, ATI times eta squared times RTI squared. And let me actually write this down because later we're going to get back to it. So putting everything together, the regret of exponential weight is at most log n divided by eta plus sum over t, sum over I, ATI times RTI squared times eta, right? So you have the 1 over eta, then there's a eta squared here that gives you eta. So this is the important bound. In the dynamic pricing lecture, we also get back to this bound. The reason I like it is some sort of like self-correcting bound or self-bounding property, meaning that on the right-hand side, the algorithm's probabilities are appearing as well. And this is usually good when you try to get multiplicative bounds. It's not what you're trying to get here. But in general, I think this is much stronger than the bound that I'm going to write in a second. So you can say this is also upper bounded by, is it bounded by 1? I take a summation over I. This is the distribution, a point in the simplex, so the summation becomes 1. So this whole thing becomes bounded by t. So this is going upper bounded by log n over eta plus eta times t. And therefore, upper bounded by a square root of log n over 2 times the square root of log n over t, if you set eta to be square root of log n divided by t. Right? And that's the bound that you got in your search. Bound number 1, bound number 2, let me show you a third bound. And then we are going to move to the main thing that we would like to study today, the multi-bound problems. And we will see how these bounds are making our life super easy there. So bound number 3, kind of a very cool bound, actually. And this is going to help us to get best of both worlds. It took me some time last night to prove a technical demo, which I'm going to show you in a second. I will leave that as an exercise because if I want to show that to you, it's going to take me 2 whiteboards. It's just like algebra. But let me show you the bound. You have a question?
Just a quick question. So it seems that the f function is like a loss function you're having, and then d is some sort of regularizer, and the entire construction of f and d has nothing to do with the reward function, right?
That is true. So the construction of f has nothing to do with the reward function. But then, so how you can, as an engineer, how you can design f to be a good f? So you should look at properties of R. Like for example, here I know R is bounded by 1. And therefore I designed f such that this bound comes up. Right? So this bound did not appear when you were using the quadratic function. Right? So it was something else, which it's different than that.
We know properties of R can be designed like f's depending on R.
Yes, you should look at my job market paper now. That's exactly what I did in my job market paper. So I had a dynamic pricing problem where you should think of it as a multi-arm bandit where the reward ranges for different arms are different. So for example, one arm has a reward range which is between 0 and 1, the other one between 0 and 10, the other 0 and 100. And then the question is, what would be an online mirror distance that gives you a regret bound that scales linearly with respect to range of each arm when you're comparing the algorithm with the reward of that particular arm. And then it gives you an optimal bound for dynamic pricing. It matches the sample complexity bounds of the pricing. So that was kind of the reason that we used OMD to incorporate inside information of the reward structure in the design of the algorithm. And then the mirror map that we have is using those ranges. It's a multi-scale version of negative entropy that you multiply each term by the range. And it turns out that's going to work. I was planning to talk about that paper, but we'll see if I have time. Not today, in one of the future lectures. All right, so go back to our stuff. Bound number 3, this is, I think, a very useful bound. And the reason I like it is because maybe you have already observed that. Many times I'm talking about online mirror descent, even though I never said this mirror map should be decomposable across coordinates. It is actually a separable function. It's summation of a bunch of them. And this is not by accident. there is a way to generate mirror maps from potential functions. Potential functions are, so this bound comes with a couple of explanations. The potential function, think of it as a scalar function phi that maps R to R and has all the properties that we expect from a mirror map, which means phi is strictly convex. Limit of phi prime of x when x goes to say infinity or absolute value of x and phi prime of x, then x goes to infinity is actually not infinity. Right? So these are basically equivalents of the same property that we expect for mirror maps when you think about one-dimensional versions. And now given a potential function, I can define its corresponding mirror map. So f of vector x is going to be the sum over I phi of xi. Okay. Now, the bound tree is going to tell us a bound when you look at this particular function of this, when they are separate. Let me write the lemma that took me some time to prove. Maybe it will be easier for you guys. Let me tell you how did I start thinking about this lemma. I actually didn't find. If someone knows a reference for this lemma, please let me know. I'm not sure if it exists anywhere. So here's a known lemma. I'm going to write that one. The known lemma. And it's not useful for our application. Suppose f, or in particular, yeah, actually f is mu strongly convex. And because I'm not going to use this now, I'm not going to tell you exactly what does that mean. So if you don't know what is strongly convex, just tune off. Feel free to not listen to me in the next 2 minutes and then tune back. So f is mu strongly convex, then 1 f star is going to be 1 over mu Lipschitz smooth. And then the second property is about Bergman divergence of f star. The df star of x and y is going to be upper bounded by 1 over 2 mu x minus y squared. Actually, ChatGPT gave me this lemma. And then I found the source last night. But ChatGPT couldn't give me the lemma of the reference of the unknown lemma. I had to sit down and prove it. And I didn't find it by my search as well. So this is the unknown lemma. I'm not sure if it's unknown really. Unknown lemma. If f is separable, then the f star of x and y is at most summation half times summation I from 1 to n, 1 over p double prime of p inverse of xi, p double prime of always confusing. So p double prime of phi prime minus 1 of yi. Maybe there is a better way of writing this one by the way. I don't care if there is. All I care is this form is what I'm going to use. Times yi minus xi squared. So in other words, this is really like the analog of this. But rather than having a strong convexity assumption, which gives you a bound on a lower bound on phi double prime, and therefore an upper bound here, I'm using a specific function form. It turns out that this actually helps. So it is the phi double prime. The input argument is phi prime inverse of yi, which is something like 1 over phi double prime of phi inverse yi. But let's keep it like this. I'm not sure if there is a simpler form actually, because this is inverse of the first derivative. And the inverse is well defined because I assume it is strictly convex. So therefore its first partials are monotone, therefore monotone increasing. And therefore this is well defined. Now, using this bound, here is what I'm going to show. Bound number 3, the regret of mirror descent. With respect to some arm A is going to be upper bounded by FA minus FA1 divided by eta plus eta over 2, sum over t, sum over I, RT I squared divided by phi double prime of RT I. Oh, sorry, ATI. That's not a question. And just for a second, if we stare at this for a second, if you multiply by ATI divided by ATI, use exponential weight, this is exactly the bound that we had before. You should really think of it as a generalization of that earlier. Let me show you why this bound is true. And then we are going to switch to the more fun part. So all I'm doing is using this bound for the local, right? So proof initial divergence as before. For local norm, we can say it is at most summation over 1 over eta, summation over t. Right? So then we have the df star of the two vectors, because df star of x and y is upper bounded by this quantity. I can say it is at most half times summation I from 1 to n, 1 over phi double prime of phi prime inverse of my yi. So if you remember what yi was, it was actually gradient of f at the point a t. But the ith component of that is, which is nothing but just really phi prime of ATI, because of the fact that f was a separate function, right? So if I look at the gradient of f with respect to the ith coordinate, it's going to be phi prime at that input, so it's going to be phi prime of ATI multiplied by the L2 norm of the distance, yi minus xi squared, which is already eta squared RTI squared. That's exactly the amount that I had before, right? So this is gradient of f wt plus 1 minus gradient of f at coordinate I squared And then the rest is what I had as before. Now you see that this becomes phi double prime of ATI and therefore. Is it clear? So I use the lemma. Lemma. And use the bound that we had before on the local. Right? Cool. You will be convinced that it is useful, but only at the end of the lecture. For now, let me just continue. And let me introduce the multi-arm bandit. So multi-arm bandits with finitely many arms. It is exactly as before, with the following difference. In full information, after learner picks AT in delta n, the entire vector RT is revealed. In bandit information, or other bandit information, after learner picks AT and in particular selects, let's say, IT drawn from AT, then I see RT of IT. So only the reward at that arm that they selected is revealed to the learner. There's a weaker notion of partial feedback, which turns out to be equivalent because somehow you can repeat sampling, but I'm going to stick to the stronger notion. So the weaker notion, which is not really weaker, is the learner actually observes AT dot product RT. In other words, you observe the expected reward that you could get with that function. All right. So now the first shape problem can be designed on. Let me erase the part. So the main principle for designing multi-arm bandit algorithms is the very well-known principle of exploration versus exploitation, which basically means that you want to have an algorithm that is more or less a greedy algorithm, therefore it does a lot of exploitation. But at the same time, occasionally, for the sake of learning about other arms, it's going to do exploration, which we should really think of it as picking a random arm, maybe. The most exploratory move ever, that's you just pick a random arm to learn about something that you don't know about. And now the question is how we can use this principle. So main idea, very high level idea, is combining exploration with exploitation. So what does exploration mean? Selecting an arm that is not only informative about that arm, but also informative about the other. That is informative about that arm and also other arms, potential. Or maybe selecting a strategy for picking arms, such that strategy is spreading the information that you get across many arms. For example, uniform distribution across many arms is a very exploratory strategy. And then exploitation is completely opposite, basically based on current historical information. Selecting the arm that looks good. Right. Quite simple, seems simple. And now there are many strategies that you can start thinking about to design bandit algorithms that they do exploration and exploitation. So there is one that I really like, I think, because it's simple, and at the same time, it reveals a lot about underlying challenges when you're facing a multi-arm bandit problem. So I'm gonna talk about that strategy. And then we will see that that strategy can be reshaped into another one, which is actually a good algorithm for multi-arm bandit, but still not the optimal algorithm. And then later we're going to shoot the machinery that we learned on linear descent to get the optimal algorithm. So here is my first attempt suggestion. People have different first attempts when they think about multi-arm bandit. A very famous first attempt is epsilon green, which is you flip a coin at random with some frequency, which flips heads, then you're gonna pick an arm uniformly at random. If it flips tails, then you're gonna go with a greedy arm. And this strategy is also gonna be a good strategy. So the one that I like, I think, is revealing more about multi-arm bandit is this thing called phase simulation. Let me write it down. And then I'm going to explain the basic idea. So this is how I think of phase simulation. So suppose you're running a multi-arm bandit problem. You're running an online algorithm in a multi-arm bandit setting. And then somehow at the end of each round, magically you have access to an estimator of the reward in that round. Right? So what does the estimator mean? Think of it as a randomized estimator that maybe is an unbiased estimator of the real reward. For example, the full information, you actually have access to that unbiased estimator because you get to see the reward, right? Now, suppose somehow magically you have access to such an unbiased estimator. Then you can say, well, so I can feed these unbiased estimators to a full information learning and think of this hypothetical scenario that there is a full information learning algorithm that plays with these unbiased estimators. It's as if the environment itself is shooting with the unbiased estimators as the true reward. And then I try to use the guarantee of this full information learning algorithm to say something about the multi-arm bandit. But then the question is, okay, so how can I have unbiased estimation? What does that even mean? Like, I haven't yet even tried playing with the arm. How on earth I can have unbiased estimation? So here's like the most naive way of creating an unbiased estimator. Suppose you have some number of rounds, right? Let's say round 1, round 2, all the way to round n. And somehow after you make a decision, let's say you get to see these results. So R1, R2, RL. All right. So the goal is somehow having an unbiased estimation for the average reward in this epoch. Think of it as an epoch of decision making. So I'm going to look at the vector R bar, which is 1 over L summation all the t's in this phi. Let's call these episodes to be phi. T in phi, the vector RT is the average reward vector. And somehow, as a decision maker, let's say at the end of this epoch, by minimal amount of exploration, I would like to have an unbiased estimation for this average.
If you're playing one action here.
Let's say you can play just one action, then what would you do? So if you can play one action, then you can probably get an unbiased estimation for one of the coordinates. And here is the simplest thing you can do. Think of basically picking a random time, and in that random time playing action I. So if I pick a random time and then I pick action I in that random time, then what happens is that what is the reward that I get in expectation is going to be exactly the reward that R bar would have received under that action. Right? Why? Because the probability that this guy is my selected time is 1 over L, this guy is 1 over L, this guy is 1 over L, blah, blah, blah. So then the expected reward that you get by playing fixed action I in that random moment of time would be basically the average reward. But then we have n arms. So we want to get an unbiased estimator for the whole vector. So now let's do this for all arms separately. So I'm going to define, let's call it explorator. Explorator mapping tau that really think of it as a map from arms to times in phi. And really think of a random assignment, random 1-to-1 mapping from numbers 1 to n to times here. So this explorator is going to be a random 1-to-1 one-on-one mapping. From set of arms to phi. So now what does that mean? So if I look at tau 1, tau 2, blah, 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 to tau n, these are n spatial timestamps that if I get there, so and as a decision maker, I go over these rounds one by one. So if I get to tau 1, I'm going to explore arm 1 by just pulling arm 1. If I get to tau 2, I'm going to pick arm 2. If I pick tau, I get to tau n, I'm going to pick arm n.
Does this randomization here help? So we can just play arm 1 or
It
like
helps because if I, for example, if I do round robin, right? Well, so if you just like want to pick n things, right? So if I deterministically pick them, then by no means this is going to be an unbiased estimator.
Oh, here you assume the distribution of reward can change.
Yes, it is adversarial setting. Right. Importantly, it is the adversarial setting. I'm so sorry. Is that clear? So I'm looking at the randomized mapping from numbers 1 to 5. And now marginal distribution of each of these guys would be uniform random between 1 to f. So if I take expectation from the reward I get by exploring that random time, that would be exactly equal to RTI. In other words, I'm just saying, if I look at R at time tau I, coordinate I is the random variable. The reward that you get at time stamp tau I for arm I, because you are playing arm I in that round. Then the expectation of this random variable would be 1 over L summation T in phi RTI. And that's essentially the R bar that they had at the coordinate I. So this is great. That means with kind of like minimal cost in a phase, you can get an unbiased estimator for this guy. But well, so once you're making decision for this epoch, you can't have that unbiased estimator. So you can have the unbiased estimator only after, right? And then you can say, well, maybe actually this epoch was really like a discrete round. In another problem where I'm playing in epochs, epoch by epoch, and then this is the full information in some sense, because at the end of that epoch, you have an unbiased estimation for that epoch. So then you can say, hey, let's think about the full information on a learning problem, slight variance where rather than getting the actual reward, I get an unbiased estimation for my reward, but in that new instance, rather than having capital T number of rounds, I'm going to have some number of epochs, which is equal to T over L, because each epoch has length L. Right? And then that strategy suggests that during each epoch, during each phase, you want to select the same strategy, the one that is suggested by that full information. And that brings us to phase simulation. So, phase simulation algorithm. I think we have Oracle access to some algorithm for full information multi-arm maps. Let me call it ALG full with some learning rate parameter eta, such that the regrets of ALG full for any problem instance, as long as the rewards are between 0 and 1, up to any time t, will be at most something like what we had before. So log n divided by eta plus eta times t. Right? So that's the bound that we had, the best bound for full information. Yeah, suppose you have access to such algorithm. It can be exponential based, it can be maybe follow the perturbed there, it actually gets the same bound. It can be follow the regularizing there with log barrier as the mirror map, etc. There's a class of algorithms that we can get this full information figure bound. Now, what I'm going to do is the following. So I'm going to divide the time, into p phases of length L. And I'm waving my hands by assuming that T is equal to PM, but don't take me what would you do if, for example, T is not divisible by P or L. I'm going to change my claim, change my L. I might add some dummy times at the end. So somehow without associated, you can assume T is always equal to PM. Now you have these phases. Phase 1, length L, phase 2, phase 3, phase T. All of them, they have the same length L. Let me define a notation. So I'm going to use notation R bar of J, think of it as the vector, as the average reward in phase J. It's going to be equal to summation 1 over L, all the T's in phase J. And let me call this guy phi1, a subset of time. This is going to be phi2. This is going to be phi3. This is going to be phi p. So all the T's in phi j, and then look at the vector RT. Okay. Now the algorithm is going to do the following. So at the beginning of phase J in 1 to P, I'm going to send a query to that full information on learning algorithm, ask the algorithm what should I do in these things. So send a query to that full information on learning algorithm and full. And let's say this algorithm returns with a strategy, distribution arc, let's call that AJ hat, and this is basically a vector. Right? It is a distribution over n arms called AJ hat. Then I'm gonna keep doing the following. So 4 times t in phi j, so you have the times in phases if time t was an exploration time, which means that times t was equal to tau j I for some I. And these mappings, you should really define them at the beginning. So I have one explorator for each phase separately. And imagine these are independent explorators, so they have separate random points. So now, if time t is equal to tau j I for some I, I'm going to select I t to be equal to I. So basically, I'm going to explore. Otherwise, I'm going to listen to the full information algorithm decided on a strategy for this phase. So I'm going to realize IT from the distribution AJ, and then you continue. So this is basically the outcome. Any questions about what this algorithm is? Pretty straightforward. Target phases. I have a randomized explorator for each phase. They have independent randomness, so they're operating independently. They decide which rounds are the exploration rounds in some sense. And then at the beginning of a phase, I send a query to, I didn't say how to update this query. So I send a query to the full information learning algorithm gives me a strategy. Then if I'm at some time t, it is the exploration time because the explorator told me that this is the right time to explore arm I, then we'll select arm I. Otherwise, I'm going to listen to the full information learning algorithm and randomly draw an arm from distribution AJ hat. Now it is the time to keep this guy updated, right? Because it's a full information learning algorithm. And imagine so this guy and the pool has P rounds, important. So really like it's an algorithm that is run on the phases. So at the end of each phase, it gets that, right? The vector of R tau I, for I from 1 to n, as feedback, as full information, important as full information. Ideally, I wanted to give R bar, the actual R bar, as feedback to that algorithm, but that is impossible because you could not explore in all rounds so that you can get R bar. However, you explore the random subset of rounds, those corresponding to the round selected by the explorator, and you have formed some unbiased estimator for the average reward in that epoch. Give that as the full information feedback to alpha.
This is from time 0, right? From time 0, whenever you explore, you use that reward.
No. So I will only talk to this algorithm P times. That's important. P is number of phases. So the first communication happens at the beginning of phase 1, and then the second communication at the beginning of phase 2, so on and so forth. At the end of each phase, however, I have to send the feedback about that phase to that algorithm. So the feedback is going to be the reward I accumulated using my explorator in that phase.
The question, my question was, why do you use just in that phase? So you explore sometimes from beginning, right?
Right. Why should I not look at all the
yeah.
Because this guy requires an unbiased estimation for the reward of that phase. Why should I include the previous phase?
So I think what I didn't understand is how the distribution of reward changes over phase.
Let's think of it in this way. Think of a full information adversarial online learning problem where you have a discrete round for each phase, and your reward is R bar. So if you want to run an algorithm for that problem, what would you do? Exactly as we did in the lecture, right? At the end of each discrete time, basically each phase, I have to tell you what the reward of that phase was for all the R's. And this is essentially the feedback that this type of algorithm thing needs. and I need to provide that feedback.
Yeah, I don't care about the.
You don't care about the past. Like, for example, when you're designing algorithm for the best expert problem, you don't tell the algorithm what was the average reward from the previous round. Just like say, hey, this was the reward that was decided by the adversary for that particular round. And you have to design that feedback for this. But it is important that it is part of your design. It's not selected by the environment. The environment is selecting ours. You, as the algorithm, are using this full information understanding algorithm as a subroutine, and you have to feed it the right feedback by the means of using that explorator defining the feedback. Is it clear what you are doing? All right. So let's try to analyze this algorithm. It's actually pretty easy, and then we can have a break and see how to get better bounds and the best bounds and best of the both all in one shot. How to do that? Let me go with some basic definitions. Just notation. Explore I. These are the subset of rounds in which we are exploring arm I throughout the horizon. Basically, these are all how ji's or j from 1 to p. Does it make sense? And then I'm going to define explore. So this is a subset of 1 to t. So explore is going to be the union of all these explore i's. I from 1 to p. Again, the subset of 1 to t. And then I'm going to define exploits to be basically all other rounds. Capital T minus explore. So funny. So one of these board markers is the better one. And I'm running a multi-arm bandit algorithm on which one is the better one. That fixed arm, that's fixed board marking concept. Right. And so roughly speaking, we expect the following. So we expect that we are not losing that much in terms of rewarding those exploration rounds. And then we have accumulated enough information so that in exploitation rounds, we're also not losing that much. And then we are trying to find these two quantities, their contributions to regret, and see what that would look like. Then we decide on the learning rate and L and P to optimize the final. So let's do the following. So we already proved this now. Let me write it down for completeness. If I look at the expectation of, and let me pick a name for this guy. So expectation of, should I call it R hat? Sure. So R hat of J, condition on the history before J, this is basically equal to Rj bar. And what is R hat J? So R hat Ji is defined to be R at time tau Ji. So tau Ji at coordinate 8. Right? So the reward that you get in the exploratory round tau Ji corresponding to R, because you explore R. I claim that this expectation is called RG1, and we already solved it. Now, what's the reward that the algorithm gets? So the reward of the algorithm, let's say all the exploitation. So, so reward of the algorithm is definitely more than the reward that you get in exploitation, right? The sum over all the t's that are part of the exploitation. And then in all those rounds, you get some AT dot product out, which you can write it down as sum over all the phases, let's say J from 1 to P. And for a reason that will be clear soon, let me actually divide everything by T. So I'm looking at the average regress. So this is going to be 1 over T. Then you can write it down as 1 over P times 1 over L. All right, and then we are looking at all the times in phi j such that T is also an exploitation round. I'm getting rid of the exploration for now. And then in all such rounds, AT is basically AJ hat, right? Because if I'm in a phase J and it's one of the exploitation phases, then I'm going to listen to the full informational learning algorithm that gave me a suggestion at the beginning of that phase. So my strategy is going to be AJ hat, and this value is going to be multiplied by RT. Now, let's do the following. So what I'm going to do is I'm going to add the remaining rounds that I had in this summation. So this summation has exploitation rounds and a bunch of exploration rounds. Let's actually add back these terms for those times as well, and then subtract those. So I'm going to say this is going to be at least, let me write it down, and then I'm going to explain 1 over P summation J from 1 to P, 1 over L, sum over now all T's in phase J, AJ hat, dot product RT. All right, so I added a bunch of things here. And how much difference you have at most? It really depends on the, so in every such round, exploration round, you're going to lose at most 1. How many exploration rounds do you have? That's number of phases times n. And you're dividing by a t, so it's going to be minus n times p divided by t. What did I do from here? Just imagine for a second this summation was over all the times in phase J. So the only thing that is not included are the exploration rounds. In those exploration rounds, this dot product was at most 1. And how many of those exploration rounds we have in total? N times P, because you only explore N rounds in each phase. So N times P divided by T. And then you get this. And this is equal to 1 over P, summation J from 1 to P, AJ hat dot RJ bar. Minus NP divided by T. So somehow we connected the regress of our algorithm to the reward of the algorithm to the reward that the full information algorithm gets if the feedback was RJ bar. But the feedback is not RJ bar, it is RJ hat. So we know in expectation is the same thing. So this is equal to expectation of summation J from 1 to P, 1 over P, summation J from 1 to P, AJ hat dot expectation of RJ hat condition on H smaller than J minus NP divided by T. Right? And then I can just remove all these expectations, put everything here. So it's going to be expectation of 1 over P, summation J from 1 to P, AJ hat times RJ hat minus NP divided by T. Right? It's pretty simple. Now this is good because this is exactly the expected reward that the full information learning algorithm receives in the game where the environment is shooting RJ hat at the end of each phase, not RJ bar. And this was exactly the feedback it received. And now I can invoke the proper regret guarantee of this full information algorithm and then say something about that term. So let me do that. And then we can take a quick break. Therefore, my reward is going to be at least, let me write it down, 1 over p summation j from 1 to p, aj hat dot rj hat in expectation minus np divided by t. This is divided by t. And now, using the regret guarantee of full info algorithm F, I can say this is at least, let's say pick some arm I, right? So it is at least 1 over p summation j from 1, let me write everything. So 1 over p expectation of j from 1 to p rj hat I. All right. Minus my regret bound, which is log n divided by eta. Don't forget to divide by t because we are dividing by t is average regret. Plus sorry, divide by p, right? Because you have p rounds in that problem. I'm looking at 1 over p times the reward that you get. So log n divided by eta p plus eta. And then minus np divided by t. Is this clear? So I was saying now, because of the regret guarantee of this algorithm, think of the average regret guarantee of the full information on an algorithm with p rounds. So it's 1 over p. So therefore, 1 over p times the expected reward that you get is greater than 1 over p, but every fixed action can get. So this is true for every action I in N. Minus the regret term on average, which is log n divided by eta divided by p plus eta times p divided by p, which gives me this. Now I'm going to invoke the unbiased estimation property again, but this is going to be equal to, and bring expectation in rj hat I, and expectation will be equal to rj bar I. So 1 over p summation j from 1 to p rj bar I minus log n divided by eta p plus eta minus np divided by eta. And this is, now we can expand this. This is going to be exactly equal to 1 over t summation t from 1 to capital T r t I. Because this is 1 over L, right? So this is 1 over L summation t in phi j r ti. So therefore, everything is going to be 1 over p times L times summation over all the time. That's the quantity we get minus this thing. So this is the regret bound. And we have to design 2 parameters this time. One is learning rate, eta, and then the other one is the number of phases, p. Let's do that. This algorithm has the best dependency on the number of arms among all the algorithms that I can show you. But unfortunately, it will suffer from suboptimal dependency on T. And let's see that. So we have balanced terms. So let's say I'm going to pick eta such that these 2 terms are equal to each other. So this is minus. Such that these 2 terms are equal to each other. And then I'm going to pick p such that all three are equal to each other. That means I'm gonna select eta to p, bear with me a little bit, I'm a little bit slow in this thing, square root of log n divided by p. If I do that, then I have to equalize the square root of log n divided by c by n. So I have to equalize log n divided by p with n times p divided by this. So this is like n p to the power 3/2 divided by square root log n. I hope I have not made any mistakes. Does it look?
Yeah, that's right. But I think it was better if you started with P because P.
Let me follow power suggestion. I think they're equivalent, but I think he's saying that if I should start from P, so I'm going to set P to be eta t divided by n. Is that what we're going to do? Right, I think so. In that case,
The square root. No, that's.
now I have to equate eta times t divided by n. Now, so p gotta be eta times t divided by n. Then we are gonna equate eta. So now I'm gonna have eta squared to be equal to log n over p, and that's p, so log n over eta t times n. So that means eta would be equal to n to the power 1/3 log n to the power 1/3 divided by t to the power 1/3. And this is essentially your regret bound. So basically, your regret bound on average is equal to n to the power 1/3 log n to the power 1/3 divided by t to the power 1/3. And therefore, your actual regret bound is going to be as smallest order t to the power 2/3 n to the power 1/3 log n to the power 1/3. Right. So let's have a break for maybe 10 minutes, and then we are going to be back and see how we can actually get an improved figure about this.
It should be N over T. No, left.
Here?
Down. No, left whiteboard.
Left whiteboard.
Yeah. Down. The last. Yeah.
Oops. But that's
That-
correct.
No, but that.
No,
should
because
be
you
it.
were using the.
I was actually looking at this
Yes.
line. I was looking at this line and I got the
Yeah,
correct.
so that's fine.
Right, that's fine. I made a mistake in this line.
Isn't the optimal thing just the square root of that? Or-
I don't think so. So I want to equate all three.
Yeah, exactly. So you wanna equalize NP divided by T
It's
is one
eta.
over eta P.
I mean, you can do the hard thing, you can do the easy thing, which is what I did. So equate this and that. So everyone has a break. So you can do this.
Right,
You can
very good.
continue. More distracting. Don't look at that. All right. So here's what we are going to do. The goal is really trying to get a better result. And then the first step is changing our design, but still like following the same type of approach as say simulation. And trying to see if we can get a regret bound that has a better dependency on T. And before getting there, let me actually tell you about the lower bound. I'm not going to show that lower bound, but I'm going to mention it. It's important to know. So theorem. it goes back to the work of Peter Auer et al. Title of the paper is kind of interesting. Gambling in a rigged casino. 1998. And the lower one is basically the following. So in Adversarial multi-arm bandits, any algorithm has regret of p omega square root n times t in expectation. Maybe that's a lower. So you can't hope to get anything better than square root nt. And then the bound that we have actually has a better dependency on n, but it doesn't have the right dependency on t. And in some sense, I think getting the right dependency on t is the first order objective, and then after that, we should get the right dependency on. So now, here's one way of trying to improve that algorithm. I think that when you think about that algorithm, remember, so the regret had two parts. One was coming from the full information, the other one was coming from the phases and the exploration loss that you have. If somehow you can explore less, or let's say you use less number of rounds for exploration, or in other words, you do exploration more effectively, you should expect to get rid of that last time and somehow make the bound pretty close to the full information bound. But definitely because of this lower one, you should not be able to get a bound that is exactly a full information bound, because if you could do that, then this dependency on n would have been log n. That's what we get in full information. So there should be something there. But I think like one question is, can I do exploration more effectively? Can I use less number of rounds to do exploration and then hope to get the result I want? And in the design I told you about, L, the number of lengths in a phase in order to do exploration, should be at least n, right? So you can't hope for exploring about all arms using our randomized explorators if you have less than n number of rounds in the way that we talked about it. One question is the following. Can we explore when L is equal to 1? So just give you one round, can you actually explore or have a little bit of exploration? And this idea, which is a prevalent idea in statistics, is genius. I think it's the core of why we can have algorithms for multi-arm bandits that they have the right dependency on t, and that's using an estimator, unbiased estimator for the reward that only requires one round. That brings me to this definition. Weighted importance sampling. And the idea is super simple. Suppose we have a distribution for selection of an arm. Suppose I is realized from some distribution A that is in n-dimensional simplex. Then weighted importance sampling or sampler of the full information arm is defined to be the following vector. So it's going to be a vector. Let me use a convention. Let's call that R hat, which is an n-dimensional vector. So it is a vector in 0, 1 to the n. Not necessarily 0, 1. So let me go with R plus to the n. And then what do I know is that R hat of I is defined the following way. So it's going to be equal to basically the reward that you get from this exploration, let me actually use a different motion I had. So R hat of I is going to be equal to R of I indicator that I hat is equal to I, but there is a term that I need to write. Let me explain what I'm doing. So you have n different options. You select one of them from a distribution A. Let's say you pick I. Then I'm just going to say, hey, I'm going to create a vector that for every arm that you have not selected, you have 0. And for the arm that you selected, the reward is equal to the reward that you use. So this seems to be an estimator for your actual reward. But it's not unbiased. In order to unbias, you have to correct for the probability that you select different arms. So therefore, I'm going to divide by A of I. Right. And this is basically my estimator. It's called weighted importance sampling. So just given any distribution, if you look at the outcome of the distribution, you can actually have an unbiased estimation for the reward of that, regardless of what that distribution, how exploratory that distribution is. And here is a demo. The unbiased estimator property, unbiased estimator. Expectation of R hat I is equal to Ri, or every I. Why? The proof is super simple. So expectation of R hat I is basically equal to Ri divided by Ai times the expectation of the indicator that I hat is equal to I. And this happens with probability Ai, so it's going to be Ri divided by Ai times Ai should be equal to 1. Very simple. Now, what we are doing in phase simulation, we were designing unbiased estimators for phases, and then we were feeding them to a full information on a learning algorithm. That's great. But if n is equal to 1, I can do that on a round basis. Like at the end of each round, regardless of what you're playing, you have an unbiased estimation for the reward of that round. Just feed that to a full information on a learning algorithm and see what that online learning algorithm is suggesting and play that in the next round. Exactly phase simulation with n is equal to 1. The only difference is that in one round, I'm going to use weighted importance sampling. Also, now you can use your favorite full information online learning algorithm for this practice. What I'm going to do is I'm going to use the most powerful full information algorithm that we have learned so far. That's unlinear descent, and that brings us to the stochastic OMD. And then you can think of the learning rate and mirror map F as the internal parameters. And then this word OMD, depending on F, can be replaced with its special case. For example, if F is the negative entropy or the generalized negative entropy, this is going to be a stochastic exponential base, also goes by the name of EXP3. If F is the norm 2 squared, then this is going to be a stochastic online gradient descent. That's basically a stochastic gradient descent, but the online learning variant, and so on and so forth. Right? If this is the most general class, and it is as simple as you can imagine. For t from 1 to capital T, I'm going to do the following. So I'm going to ask OMD what to play. It gives me a strategy, let's call it AT. Then I'm going to play arm IT drawn from AT. So therefore you observe the reward RTIT. Then that's R hat at time T for every I to be equal to, or in other words, RTIT to be equal to RT hat IT to be equal to RTIT divided by ATI. This is something that was in your position. And our hat T of I to equal to 0 for every I that is not equal to IT. So this is basically weighted importance sampling. Now feed the vector RT hat to OMD so that it does this update. So OMD does updates, which basically means the gradient update combined with the projection. And then we continue. That's it. Okay. All right. Let me try to use whiteboard more efficiently moving forward. I have a picture in my notes. They like that picture. They like pictures. This is my picture. Imagine this is full information OMDs. This guy is suggesting us AT at every round. Then there is the environment. That decides on the vector, generates RT of IT, and imagine IT is actually a sample from IT. And then we have this weighted importance sampler that gets this input and generates the vector RT hat. And this whole thing is called the stochastic linear. But importantly, there is an underlying full information learning problem hidden here. And that's when you look at the world from the perspective of this full information OMD. So if I look at this full information OMD, what's really happening is that imagine WIS was part of the environment. So you are interacting with the environment, sampling an R, and then the environment is feeding you some feedback, which is RT hat. And then you play. Right? So from this perspective, the full information learning. And now we are hoping that the fact that this estimator is unbiased is going to help us to carry the guarantee of the full information and near descent to a stochastic analysis. This is exactly what we're. Right. So let's do that. Let me start by writing down an expression for regret. The regret of my OMD, not the stochastic OMD, OMD with parameter F and eta, right? So this is equal to what? So it is equal to, let's say, with respect to arm I. Arm I for a strategy A, it's A in delta M. Then the regret is that equal to summation T from 1 to capital T, RT hat dot product with A. And I'm looking at the environment without the WIS wrapper. So think of it as a wrapper around the OMD. I'm just like looking at OMD, the thing that it receives and the action it plays. So in that word, this is going to be the reward of playing a fixed action A in all rounds. Minus what the algorithm is, summation T from 1 to capital T, RT hat, dot product with 8. Okay. At the same time, we know that this regret bound is upper bounded by, let me use some of the bounds that we have. For example, just for demonstration, let's say we use exponential weight with learning rate eta. Let me write it down and you tell me if you agree. So it's going to be L log n divided by eta plus eta summation t from 1 to capital T, summation I from 1 to n. And then we had ATI, if you recall, times r hat Ti squared. Do we agree? This was the expression that I had in one of my bounds, bound 2. So this is the left-hand side. This is the right-hand side. Let's just take expectation. Therefore, my expected, right, so let's take expectation. So if I take expectation from this side, what would happen? So you can take this expectation in stages. So if I take expectation of this thing, the expectation of left-hand side would be, okay, so expectation of RT hat is unless symmetry is equal to RT, so it becomes RT, the summation T from 1 to capital T, RT dot A, this is good. What about this guy? So I can take the expectation in phases, right? So that means that I can take expectation in the following. So expectation summation T from 1 to T, expectation of RT hat dot AT, condition on history before time T. So that's the notation I'm using for history. Back to your question in the bridge. Right, so now the good thing is that if I'm conditioning on H smaller than T, AT is deterministically known because I didn't want to restrict myself to a class of deterministic algorithms. You, in principle, you're allowed to pick a distribution or distributions if this is something helpful. It's not very helpful, but I'm not going to restrict you. But regardless if I condition on the past, it is an online algorithm. Therefore, this quantity is going to be deterministic. It does not depend on anything. Or let's say it is very independent on RT hat. That's a better way of phrasing it. The randomness in RT hat now is going to be decoupled from randomness from RT in AT. So therefore, I can write it down as simply summation over T, RT dot A minus. So this is going to be the expectation of RT hat, condition on the past, times AT, or dot product AT. And this is because of the unbiased estimation is equal to RT. So minus summation over T, expectation of summation over T, AT dot product. And that's it. So left-hand side, your expectation is equal to the regret bound of your multi-unbounded algorithm. But about right-hand side, that's even easier. Expectation of right-hand side is equal to log n divided by eta. Now the expectation goes all the way in. So plus eta, let me do the same trick as before. Summation over T, summation over Y, expectation of ATI, R hat TI squared, condition on the past. All right. So let's focus on this thing. So this is going to be what? So it's going to be ATI times, so RT hat, you remember, right? It is RTI divided by ATI, indicator that IT is equal to I. So the square root of that would be basically RTI squared divided by ATI squared times the indicator, and then I'm taking expectation to the expectation of the indicator that IT is equal to I. And this is API. So this and this cancel that, it's going to get was RTI squared, which is bounded by 1. So this whole thing is going to be bounded by 1. Therefore, my real bound is going to be bounded by log n over eta plus eta nt. This is good. If this n did not exist, you would get the full information down, but there is an n here, which should be somehow unavoidable. Maybe this log n is avoidable, but this n does not seem to be unavoidable. So by setting eta to be square root of log n over nt, we get order square root n log n times t. So up to a log n factor, it is matching the Auer et al. Lower bound. Right. Now the question is, can we do better? And let's use our knowledge about unlinear descent and see if we can fix this.
It's empty log n, right? It's not
It's like the square root of n log n times t.
t is outside, right?
T is right, yes. Not log n t, right? Log n times t. That's what I meant. Maybe. Right, and then the issue is that, well, we need a different balance. We need a different balance. And how we can have a different balance? By changing your mirror map. And you can start thinking about different classes of mirror maps that you can try. Let me introduce a class of mirror maps that they are parametric, so you can move with the balance, so that eventually you find the right balance. And also they're kind of like simple to work with. There are other fundamental reasons that these are good mirror maps. It's got a complete class, whatever it means. There is a mathematical definition for that. So let me not go through that rabbit hole and just tell you what this family is, and let me try to see how that makes our bound better. So there is this beautiful mirror map, f of x, which is equal to the following. So it is minus summation I from 1 to n. So it has a potential form. And this is the reason I introduced round number 3. So minus summation I from 1 to n. And then you have xi to the power cubed. As simple as that. So I'm dropping that log term in negative entropy, which is actually the source of the reason that you have this log term here. And dropping that log term so that somehow the initial divergence with the right choice of q would go down. And that's what we discussed. These guys are called Tsallis Entropy. And then the algorithm that you get, if you use it as a mirror map, it goes by different names. So OMD with Tsallis Entropy. In the literature, it's also called poly-inf. If you have seen this term before, this is referring to unlinear descent when you use this function as a mirror map. I believe poly-inf refers to the case when q is equal to half, but I'm not 100% sure. I think the general case will also call it poly-inf of q. And now the question is how this will help us. Let's see. Let me remind you of another bound that we have. So bound number 3. So by the way, so the strategy is nothing different. So still I'm going to use the same left-hand side, where reaching expectation is always equal to my regret bound. The only thing is that I'm going to just use a different bound for full information. That's it. And then I take expectation. So this is basically pretty mechanical algebra. Let me remind you my bound number 3. Bound number 3. So the bound was saying that regret. Let me remind you the setup. So the setup was that I have this f of x, which is a summation of phi of xi, right? And this phi was a strictly convex function. So for example, if I look at minus xi to the power q, when q is between 0 and 1, it's going to be a strictly convex function. The square root of x, for example, is concave, minus the square root of x is extremely convex. I never said mirror map should be positive. You don't have to have positive mirror maps. You can have positive mirror maps, that's nice, but it doesn't really matter. And yeah, so it has all the properties we want. And then given this class of mirror maps, the regret bound was that it's at most regret with respect to some action A is at most f of A minus f of A1 divided by eta plus eta summation C from 1 to capital T, summation I from 1 to N. And then we had RT, I'm going to write RT hat. Why? Because we are looking at that wrapper view, right? So the environments that full information and OMD sees is shooting these guys at the feedback. So RT hat I squared, it will be great if someone tells me if I'm writing it correctly. So C double prime of ATI. That will still that. Right. And just like to compare, you see the similarity. So let me make it even more clear. So I'm going to multiply it by ATI and divide it by ATI. So this is basically the new component in the bound. Okay. All right. So let's see what we can do. Let me do some calculation. So phi of x is equal to minus x to the power q. Therefore, phi prime of x is equal to minus q x to the power q minus 1. And therefore, phi double prime of x would be q1 minus q x to the power of q minus 2.
The second term just had eta divided by 2.
Right, because I use the unknown lemma, right? That's unknown lemma that I have. Believe it or not, this half is actually important. Not for my analysis, but later when we try to get the best of both worlds, actually, I'm going to show you something, and then you guys are going to get the actual best of both worlds in your assignments, which will be released soon. Unit is half. Okay. All right, so let's now think about this. All right, so let's do each term separately. So the initial divergence is going to be at most. Let's forget about f of A. and just try to, is that what I'm trying to do? Good, so. Yes. Let's say A is a norm. So A is equal to some EI, right? So that means I'm looking at the integral vector. Their x's are either 0 or 1. For those guys, this is always equal to -1. Right? So therefore, my initial divergence is going to be -1 plus summation I from 1 to n a1 I to the power q divided by some 8, right? And then we always pick a1 such that it maximizes the negative of f or does it minimizes that. That is uniform distribution again. And then if you pick uniform distribution, what do you get? So this is going to be basically 1 over eta. Let's get rid of this 1, it doesn't really matter. So it's at most 1 over eta times n to the power minus q times another n. So it's going to be n times n to the power minus q, which is 1 over eta n to the power 1 minus q. Right? And this is a funny term. Why? Because as long as q is a constant, you're actually losing something here. You're increasing the initial divergence. Initial divergence earlier was a logarithmic term. Now it's going to be a polynomial term. But maybe you get improvement in the second term, and then you can balance this. And this is really like what's happening. So if you go with the second term, the local norm is going to be upper bounded by. I'm going to take the expectation. So it's going to be eta times summation t, summation I. Let me take the expectation. So the expectation, so this is the expectation for local norm, not clear because eventually I'm taking an expectation. Right? So the expectation of the local norm is going to be eta times summation over t, summation over I, expectation of r at t I squared times ATI divided by ATI times phi double prime at the point ATI. And then phi double prime is this function, so it's going to be q times 1 minus q times ATI to the power q minus 2. So earlier we showed this is upper bounded by one, right, by constant. Therefore, this whole thing is going to be upper bounded by eta summation over t, eta divided by q times 1 minus q, that's a constant, I'm going to bring it out, times summation over t, times ATI to the power, summation over I, ATI to the power q minus 2 plus 1, q minus 1, bring it to the denominator 1 minus q. And then each term of this form is going to again be maximized if you have uniform distribution. So therefore, it's going to be upper bounded by eta over q times 1 minus q. So this term is going to be maximized by n times 1 over n to the power 1 minus q, which is n to the power q. So eta divided by this thing times t times n to the power q. And this is really nice. Why? Because earlier, if you recall, we had a dependency, n dependency in the local norm term. Here we had a log dependency. Now what's happening when we use Tsallis entropy is that this becomes n to the power q, and this becomes n to the power 1 minus q. I'm ignoring t for now. So you make this stronger and make this weaker. This is the perfect opportunity to balance the two terms. Right? So now you guess what is the range algorithm? Q equal to half. You said Q equal to half. Now, if I go to that last whiteboard. We don't have time for rest of both words. The theorem. OMD with f of x equal to minus summation x by the power half, eta equal to it doesn't even depend on t, on n, it's 1 over square root t. 1 over square root t has the following real bounds. The expectation of the regrets. This is not a high probability bound, importantly. Is at most order a square root of nt. And then the proof is that, so we know expected regrets is bounded by n to the power 1 minus q divided by eta times, not that, plus eta times t times n to the power q. So setting q equal to half and then balancing the remaining terms. So n to the power half appears both places. So eta 1 over square root t balances the terms. Eta equal to 1 over square root t. That gives us 2 times square root nt. Right. So this is the optimal algorithm for adversarial multi-term bandits. And it goes back to my co-author Sebastian Bullock. He had this beautiful paper in 2000, I believe, 9 or 10. Basically, the paper was coming up with the Tsallis entropy as the right mirror map and getting the right. There was a follow-up paper, and there is still like some open questions here related to getting the right high probability bounds. But if you want to get the right expectation bound, which is what I showed you, that's as simple as running a stochastic linear descent with the Tsallis entropy as the. So now here is one question. I'm not sure how much of that question I will be able to cover, but let me set up the question at least, so that at the beginning of maybe next lecture, I will show you the analysis. Adversarial multi-term bandit is great. It's very powerful. It has deep connections to convex optimization and reveals a lot about how to design good algorithms here. But then there is another variant of multi-term bandits, which is very prevalent because of its practical application. And by the way, so there are so many practical applications of multi-term bandits. Or at least people like to think that there are so many applications of multi-term bandits. So for example, the one that if you go to a random talk in multi-term bandit they will mention is how to design clinical trials. Imagine that there are capital T number of patients and there is a new drug. I want to see how effective that drug is. I'm going to experiment that on different individuals to either estimate the effect of the new treatment or kind of like maximize my reward. Imagine you get a reward of 1 every time that you assign a treatment to an individual, it's successful. And then you want to kind of like find the treatment among so many treatments that has the maximum total number of successes. And that's a multi-term bandit problem. Other example is this overlay routing in networks. Imagine Mohammed Reza is in another city, I'm here, so we're trying to have a communication route. I send the packet to Mohammed Reza, and then there are different networks that I can use, or different paths I can use, different VPNs I can use. And then what I see is the delay. And then over time, I will decide on which path to select so that I minimize the delays. That's another example of a multi-armatic problem, because you don't get to see the delay of all the paths. You only get to see the delay of the one path that you select. And then in recommendation systems, it has application in advertising. For example, let's say I'm an ad platform. There is a subset of ads, and I will show them to the user, right? There's a contextual version of multi-armatic that is very relevant there. I look at the user, the feature vector of the user, the type of the user, and based on that, I decide what ad should I show to maximize the click probability. So maximizing the click probability by selecting the right selection of the ads is an instance of the multi-armatic. And then adversarial multi-armatic is attacking those settings when the underlying environment is not stationary. In many applications, though, because of either large market assumption or even the underlying problem set of the underlying environment, you can imagine that the environment is fairly stationary. And that brings us to another class of problems, a special case of adversarial multi-arm bandit. It's called a stochastic multi-arm bandit. And this guy is going to be the problem I'm going to talk about for quite some time. Same setup as before. So setup is exactly as before. There are n arms. There are t rounds. The difference is that now for every arm I, if I look at RTIs for t equal to 1 to capital T, there are I, D, and that's it. So still there is an unknown distribution attached to each arm. So that part is kind of like the unknown part, so the bandit part. But then every time that you put an arm, you get a reward, and then the reward is just a fresh draw from that distribution. And that is essentially the previous setup. I'm just tying the hands of the adversary so that the sequence of arm rewards for one fixed arm across time would be an IAD sequence of random items. Right? And then when you set it up like that, you can always think of what I call RI bar, which is the expectation of RTI. Doesn't matter which T you pick because it's IAD. And then you can define an optimal arm, which is the arm has maximum expected reward. Right? In every single round, there's one arm, the same arm, that has maximum expected reward. So I star would be the argmax of RI bar. And for this end of it clear, let me define the gap with respect to this arm, delta I, gap of arm I with respect to I star, to be basically R bar of I star minus R bar of I. So this is the expected regret that you incur if you play a suboptimal arm with respect to this arm I star. And your benchmark is going to be this guy, the T times. So my benchmark is if I had identified the best arm in terms of expected arms, I played that in all the rounds. So the benchmark is going to be T times R bar I star. And then you can define the regret to be the benchmark T times R bar I star minus the expected reward that you get as the expectation of T from 1 to capital T, exactly as before. AT dot product RT with the notes that these RTs for a fixed I would be IAD draws. Therefore, this quantity, the reward that you can get in expectation, it can be rewritten equivalently the following ways. It is equal to the summation over all T, summation over all I's. So ATI is a probability that at time T you pick arm I, And every time there's a big arm I in expectation, the regret you're gonna incur would be equal to this guy. Why? Because regardless of the path, the expected reward that you get is gonna be R bar I. Now, if you mix match the two terms, regret can be written down summation over T, summation over I, ATI times delta I. And the goal is to design an algorithm fixing the gaps. These quantities are called gaps. Gap of RMI. And you should really think of it as the measure of suboptimality of an RMI. So the name of the game is Go fixing gaps delta I from 1 to n, obtain lower upper bounds on regrets, expected regrets. So this definition comes with a note, so this is really like the expected regret, so we actually have the expectation here. Some people call it pseudo regrets. I think this, I feel comfortable just calling this expected regret. Based on the setup that I had in this class. And you can also think about regret as a random variable, and a random variable has a distribution, so you can study anything related to that distribution. You can think of high probability confidence bounds, you can think about variance of regret, etc. So all of those notions are well defined, especially in the stochastic bandit problem. There are actually some papers that they try to understand the regret distribution. They're pretty recent, but it is a topic of a study. What we do in this class is just looking at the simpler notion, which is expected regret. And the lower bound is interesting. Raise your hand if you have seen the stochastic bandits before. I know a couple they have seen bandits before. Good. If you haven't seen it, this is actually surprising. Lay and Robbins, I believe 1995. 1985, before I was born. So 1985, they established the following bound for any online learning algorithm. Even knowing gaps, suppose you, no, knowing upper bounds and gaps. Let me forget that. So you know that the gaps are bounded from below and above by some information. That does not even help the algorithm to do better. But that's a side thing. Let's just focus on the main thing. For any online learning algorithm, expected regret. Actually, there is a universal constant. This is important. There is a universal constant which does not depend on the gaps. Such that the expected regret is at least C times summation over all I nothing I star log T divided by delta I. In some sense, what this theorem suggests is that if the arms are separated enough, meaning that the gap between the best arm and the second best arm is at least a quantity, let's say constant. In that case, your regret is going to scale with log T, which is very, very smaller than the best regret that we had seen for adversarial bandit, which is square root. So in some sense, the setting is much weaker, and therefore the algorithm can do much better. But not only that, it's not only the normal. Actually, there exists an algorithm such that expected regress of the algorithm divided by t when the limit goes to, when t goes to infinity, is actually exactly, the log t is exactly equal to that same c, summation I not equal to I star log t, 1 over root. That's quite interesting. And I'm trying to actually teach this algorithm called KLUCB, which is a generalization of the UCB algorithm. It gets exactly the same constant as in Leon Robbins, and that's, I think, interesting. But then there are other algorithms. We are going to cover those in future lectures that are more of a frequentist design, and then they can match this bound up to incorrect constants, in particular the well-celebrated UCB algorithm, the Thompson sampling algorithm. They all are shown under certain technicality regularity assumptions. They can match this bound. But then there is one KLUCB that gets the bound in the limits with the right constant, which is kind of interesting. And then when you think about those algorithms, they are heavily, and I emphasize on that, very heavily, they rely on the fact that you have a stochastic environment. They are not even well defined in the adversarial world. Like when you think about UCB, I'm going to teach that, but just in a nutshell, what UCB does is keeping track of a confidence interval around these quantities, the average around this number. So I have some samples from arms, so I can decide what is my best estimation for the reward by just adding them up, dividing by the number of samples. And then forming a confidence interval around the correct quantity R bar I, and as you get more samples, these confidence intervals they shrink and shrink, so therefore your estimation becomes more and more accurate, and then you do something with those confidence intervals. This algorithm is not well defined in adversarial environment. What does the confidence interval even mean if you don't have IID samples? But then here's the interesting part. There's an algorithm that is well defined in the adversarial world, does not rely on the stochastic assumptions at all, and it gets this bound with incorrect constant. But matches the UCB one. And I think actually the constant you get with this algorithm I'm going to show you in a second is better than UCB, but that doesn't matter. It's not as good as KLUCB. But first time I saw that, I was like, there should be something wrong. Like, and so there was a series of papers. It started with the work of Sebastian Buek, my co-author, and then there was a follow-up paper by these guys, which I was trying to understand all of their proofs. Zimmert and Selde in 2019, they defined the self-bounding property for a particular linear descent, which is the key to prove what I want to show you. And then after that, there were like so many papers, they try to use the same idea. The thing is super surprised is that the algorithm is extremely agnostic to the environment. A linear descent probably uses some structures of the reward, but it's so hidden that you can't say it's really relying on the environment. But of course, it is relying on the environment somehow. Then I thought maybe there is a complicated way it's relying on the environment. I couldn't convince myself because the algorithm gives you exactly the right bound in the adversarial setting as well. So not only that linear descent matches this bound, but also if the environment is fully adversarial, it works as good as polyinf, gives you order square root nt with the correct constant 2. That's not the end of the story. There was a follow-up work that they showed, and you're going to show that in your assignment, that same algorithm which I'm going to show you gets the best bound under an environment called adversarially corrupted multi-arm bandit setting. Think of the stochastic multi-arm bandit setting, so we have IID regards. Now, suppose you start from this setup, but then a second adversary comes, corrupts capital C number of rounds, C the given capacity, arbitrary. So that adversary eventually is going to change capital C number of these rounds, and being corruption, they don't need to be the same for different arms. You can, adversarial has a capacity for corruption for different, and can use that capacity in any way. So if C is equal to 0, that would be the stochastic bandit setting. If C is equal to capital T, it will be multi-arm bandit setting with an oblivious adversary. And that algorithm actually gets a bound that as a function of C moves in a way that when C is equal to 0, you get log T, gap dependent bound, and when C is equal to T, you get the square root T. And in fact, for a given C, there are some information theoretic lower bounds, and this algorithm is very, very close to that information theoretic lower bound. There is still an open problem whether online mirror descent can match that information theoretic lower bound, but this algorithm is pretty close to it. Yes.
Are you can also tell us like, some of these lower bounds like that one?
How to show lower bounds? I can think about that for the last lecture. Do you like to see lower bounds?
I personally, yeah.
Okay. Yeah, so lower bounds, for lower bounds, I need to teach a little bit information theory. But I think I'm happy to do that. This is something that I also interested in. You're not taking the course for credit.
My word, yeah, I speak negatively.
All right, so let me tell you what the algorithm is, and then we talk about that next time, how to show the bound, the self-bounding property, etc. That will be the introduction to getting algorithm for stochastic bandits. Best of both worlds. So what is the goal? So the goal, a unified algorithm such that expected regret as a function of t is always smaller than order square root mt. And if RTIs are IID, expectation of RTI is equal to R bar I, and gap is equal to I star R of I R bar of I star minus RI, where I star is the argmax of the means. Then expected regret T is bounded by order summation I not equal to I star log T divided by delta. Let's just take the same thing again, just want to write it down. So here's the algorithm. Algorithm. Consider a stochastic online mirror descent with, I would call it slightly modified mirror map compared to the Tsallis Entropy. What is the algorithm? So f of x is going to be minus summation I from 1 to n. And then this time I'm going to have two terms. So xi to the power q. And then I'm going to have 1 minus xi to the power 1 minus qi. 1 minus q. In particular, actually, the one that's I care would be when q is equal to half. So it's going to be minus summation I from 1 to n square root of xi plus a square root of 1 minus x. Right? So that's going to be the algorithm. Let me show the lemma. I'm going to show the lemma to you next time, why the lemma holds. But the lemma, once it holds, gives us the best of all four files. And I probably need 6-7 minutes. Is that okay with everyone? This is like the core new idea that these guys introduced in the literature to talk about it for sure. So lemma called self-bounding property. Oh, no, I forgot one thing. There's a comparative, so they use this lemma, and it's actually quite important. And they use changing learning rates, which is quite important, learning rates. So far we are thinking about eta to be fixed, but now they need eta t to be equal to 1 over square root of t. So that's the algorithm. So two components, so the new mirror map and then changing learning. So self-bounding property, suppose an unknown algorithm satisfies the following. Expected regret is upper bounded by some constant c times summation t from 1 to capital T, summation I from 1 to n, square root of ATI divided by T. And I encourage everyone to take a look at all the bounds that we proved in the lecture today and try to compare them with these bounds. And you see that they have similarities, but none of them is actually as powerful as this one. So suppose an online algorithm satisfies this, then it is best of both worlds. And this basically means that I get the goal I want. Let me show you this lemma because it's quite easy. Let me start with the IID one. In the IID setting, right? So I know my expected regret is at most 3, sum over t, sum over I, square root of ATI divided by t. That's good. So now I can say, look at this term. Square root of ATI divided by t. I claim it at most ATI times delta I plus and c squared divided by ATI delta I. Not ATI, this is t. Yeah, that makes a lot of sense. So let's think about it. I didn't say anything about delta I, that is just like some parameter. So look at this function as a function of delta I. So you set delta I to be some number, then it gets minimized. And that number is exactly the one that, so the minimum quantity here is actually this, right? So in other words, if I set delta I to be times the square root of 1 over t times ATI. It's a kind of a situation that gap is small if you as a function of t. If that happens, then this is going to be equal to that, and any other delta is just an upper bound. All right. So now I can say, and by the self-bounding property. Right. So I can take the post summation over t, summation over all I not in I star. And that's like removing one term here, which does not matter. Because that's right. So I think the original self-bounding you want to compare with everyone except I star. So imagine I star is so self-bounding property means that other algorithm satisfies the following for any choice of I star. That means if I pick any I star, then I can say my regret is going to be right? Then now here invoke the property IID and let's say I star is the best one. If I do that, then this can be upper bound by summation over t summation I star, and then I get and one other important point is a half here. Right? Because once you set C like that, the two terms are equal to each other, so you need a half here so that you have quant. Upper bounded by half times AT I delta I plus sum over T I not equal to I star, and then you have half of C squared divided by T delta I, right? So this term, focusing on that, is going to be basically summation I not equal to I star, C squared divided by 2, which is some constant, times 1 over delta I, and then sum over T of 1 over T. This quantity is upper bounded by order Ln of T. And this term is half of expected regrets. Therefore, if I move this to the left-hand side, I can say expected regrets is upper bounded by C squared summation I not equal to I star 1 over delta I. And in fact, this order is always 1. If I change it to T plus 1, it's an upper bound. So let me write it exactly like this. It is at most Ln of T plus 1. You can use the concept of law. All right. Adversarial, just application of the answer inequality. So C summation T from 1 to capital T, C I square root of AT I divided by T. So first I'm going to say summation of a square root, 60, right? It's going to be summation T from 1 to capital T, 1 over square root of T. And then sum over all i's, the square root of ATI. So this is going to be at most, if I apply Jensen inequality, sum of the square roots is at most the square root of summation divided by n, but I needed and one over n here to the modulo to the n here. All right, and this is one. So it's going to give you a square root n times summation t from 1 to capital T, 1 over square root of t. And this quantity is upper bounded by square root of t plus 1. This one I can show you. So square root 1 over square root of t. So let's say I'm looking at this quantity. So this is 1, this is 2, this is 3, this is t. So this summation is the area of these rectangles. That's at most the integral from 0 to capital T of 1 over square root of t. So this can be bounded by the square root of t. So it's going to be bounded by half square root of 2 square root of x when x is changing from 0 to t. So it's going to be bounded by 2 square root of capital T. So therefore, the whole thing is going to be bounded by 2t square root of nt. Nice. All right, so let me finish because I went over time. It turns out that this self-bounding property is the property that is satisfied by this algorithm. So what I'm going to do next time is showing you how to prove it, and then we're going to switch to simpler frequentist algorithms that they heavily rely on the stochasticity of the environment. But this one it does not. I still it gets the right. So find it very interesting.